In this video, we will look at the electric field. We are familiar with the idea of a magnetic field. It is the means by which a magnet, say a bar magnet, influences magnetic materials around it. Similarly, we say that an electric charge creates an electric field around it, and this electric field affects any other electric charges that are brought into the field. We call the charge producing the field the source charge, and we call the charges affected by the field the test charges. This gives us a practical method by which to measure the electric field. We define the electric field as the force per unit charge. So, if we take a positive 1 coulomb charge and place it in a region, if it feels a force, we say that force is due to the electric field. And the relation between them is given by this equation. Let us build a picture of the field. Let's start with a positive charge. We bring a positive test charge in and look at the force on the test charge. When we bring the test charge close, it experiences a strong force. And since they are both positive, the force is repulsion. Next, let's bring the test charge here. The force is still repulsion, directed away from the positive charge, but since the distance has increased, the force is weaker. And next, here, and so on. In this manner, we can build up a map of the vector field around the positive charge. We see that the field is strongest close to the charge, always points away from the positive charge, and gets weaker with distance as we move further and further away. Similarly, for a negative charge, we find that the field vectors point inward towards the negative charge. The electric field for a negative charge looks something like this. In this case, the field vectors point towards the negative charge, directly towards it, but once again we notice that they get stronger closer to the charge and weaker as we move further away. This diagram is an example of what we call a vector field. Let us discuss this concept a little more. This temperature map of the US is an example of a scalar field. What we have done is taken a region, and to each point in the region we have associated a single scalar number. That is, a number which could be positive or negative, and with units. The units here are degrees centigrade. This is an example of a vector field. Just as how in a scalar field we associated a scalar to each point, in this case we associate a vector to each point. The vectors, of course, have direction, and they also have magnitude, which is given by the length of the vector. You can see that the vectors are very strong over here and comparatively weak over here. This is a map of the wind across the United States. Here are some more vector field diagrams. These are the vector field diagrams for the electric field around a positive charge and around a negative charge. Once again, we see the features that the field is stronger near the charge and gets weaker as we move further away. Here's an example of a negative charge and a positive charge together. Let's note a few details. We know that this is the negative charge because the field vectors point inward towards it, and this is the positive charge because the field vectors point away from it. The vectors change direction at various points, but we realize that this is probably not an accurate diagram of the electric field, because even though the direction changes appropriately, the strength of the vector does not. All these arrows have almost the same length, which does not make sense. They should be stronger in between the two charges and weaker as we move further away. Here is another way of representing a vector field. Instead of drawing arrows at every point, what we can do is draw curves. This is again a wind map of the United States, and what we see here are field lines or flow lines. Another wind map, and now we see the relationship between the field vectors and the field lines. Notice that the field vectors are always tangent to the field lines. So, these are two different representations of the same vector field. One is a collection of field vectors, the red arrows, and one is a collection of field lines. Properties we notice are that the field vectors are tangential to the field lines, and that the field lines do not cross. Here is an illustration of the field lines around a negative point charge. In this case, we have only drawn them with a certain amount of length, but really they should extend off to infinity. As before, we see that the field is directed inwards near a negative charge. Here is an example of the field line diagram when two positive charges are brought close. We see that the field lines do not cross, instead they start repelling each other, just like the charges repel each other. So field lines can be curved, and we know, since the field vectors are tangent to the curves, that the field vector over here would point upward. The field vector over here would be tangent to this curve. Here's an example of the electric field line diagram of a dipole. That is, one positive charge and one negative charge of equal magnitude. Again, we see the field lines go out of the positive charge and head into the negative charge. We have seen how to get the direction information from the field line diagram. We just need to take the tangent to the line. But what about the strength? It turns out that the strength of the field is given by how close the field lines are, that is, how dense they are. We see that here the field lines are spaced out, so that means the field is weaker here. Here, on the other hand, the field lines are packed tightly together, which means the field is stronger here. In this way, the field line diagram allows us to recover information about both the strength of the field and its direction. This is a grass seed diagram. Grass seeds tend to align themselves along electric field lines, just like iron filings align themselves along magnetic field lines. The only trouble is we lose the sense of direction. We can't tell whether the grass seed field lines are heading into a charge or away from a charge. But even without that, we still get quite a bit of information. We can see that these two charges are connected to each other. We know that they are charges because the field lines diverge or converge at those points. Since the field lines go from one charge to the other, we can tell that they must have opposite signs. And what about this feature over here? This, we realize, is the sign of a zero field point. Here are the rules for electric field lines. Electric field lines begin on positive charges and end on negative charges. They may also come in from infinity or go out to infinity, but they cannot stop suddenly in the middle of nowhere. Electric field lines never cross. electric field vectors are always tangent to the field lines. Taking the tangent to a field line at a point gives you the direction of the field at that point. Taken together, we now realize why electric field lines cannot cross. If they did, there would be two tangents at that point, which would mean that there would be two electric field directions at that point, which would mean that if you put a test charge at that point, it would feel a force in two different directions. This does not make sense. Electric fields from different charges can add up, but they end up as just one single resultant electric field vector. And the electric field lines reflect that resultant. Final point is, the strength of the field is given by the density of the field lines. We notice that as we get closer to a point charge, the density increases, and that makes sense as the field strength increases as we get closer to the point charges. Let us consider this question. If I place a 1 Coulomb charge in the field of a dipole at point A and release it from rest, it will follow this field line and eventually reach a negative charge. Is that true or false? Pause for a moment and consider. The answer is, the statement is false. It is important to remember that the field lines do not show the path that a test charge would follow. The tangent to the field line gives you the direction of the field at that point, and so it gives you information about the force. But if I released a point charge here, certainly it would feel a force in this direction and start out along the line, but as it builds up velocity, it would eventually deviate from the line. So remember that taking the tangent at each point gives you the force at that point, but it does not give you the path that a test charge would follow. Are the two charges below repelling each other or attracting each other? Pause the video for a moment and consider. The answer is they are repelling each other. We notice the diamond shape in between, and we know that this indicates a zero field point. Since it occurs between the charges, that means that they are repelling each other, and the field vectors cancel out at a point in between them. So they are charges of the same sign. A few more final notes. One is the equation relating force Q and E can be rewritten like this. And it tells us that if we put a charge Q, a test charge Q, in an external electric field E, it experiences a force F. If the test charge is positive, the force is in the same direction as the electric field. If the test charge is negative, the force is in the opposite direction to the electric field. So positive test charges feel forces in the same direction as the field, and negative test charges feel forces in the opposite direction to the field. Finally, we consider why the concept of the field was an important revolution in physics. Before the concept of a field, physics worked on the idea of action at a distance. Let us consider 2 point charges. Each charge exerts a force on the other. The red charge creates an electric field around it, which is experienced by the green charge, and the green charge feels a force. And similarly, the green charge creates a field around it, which is felt by the red charge, and the red charge feels a force. What happens now if I suddenly move the green charge closer? Does the red charge suddenly feel a stronger force? Does the change in the force happen immediately? In the old classical thinking, that was exactly what happened. If you change the distance, the charges would feel the change immediately. But now, with the idea of the field, it's a different situation. What happens is, when we move the green charge, the field around it changes. This change in the field is a disturbance that propagates outward. a wave in the field, if you like, or a pulse. When that pulse reaches the red charge, then the red charge discovers that the distance has changed and feels a different force. So, information, such as the change in distance, cannot propagate faster than that disturbance in the field. And it turns out that that disturbance in the field can only propagate at most at the speed of light. Thus, the field concept replaces action at a distance with the idea of fields that change and carry waves and pulses. In this way, physics is once again restored to locality. You can only be affected by things which are near you. But what about this case, you say? The red charge and green charge aren't right next to each other, but they still affect each other. Not quite. What we say is the green charge produces a field, the field affects the red charge. And so the red charge is only affected by what is right next to it. If the green charge moves, it changes the field, and that change takes some time to come close to the red charge. And only when it reaches the red charge does the red charge feel a change in the force. This is how the field concept replaced the idea of action at a distance. That's all for this video. I'll see you in the next.